From what we have seen in lecture 4.4 and 4.5, we have seen that if a vector is a linear combination of other vectors, and these vectors belong to a set S, then we can drop the vector that is linear combination of the others, and the set of all linear combinations will remain unchanged. So if S in V is a set, this is a vector space, and there exists W, W1, Wn, all in S, such that W is a linear combination for I that goes from 1 to n of lambda I Wi, then the vector space generated by S is the same as the vector space generated by S minus W. So we can drop W from S and still we have the same vector space generated. Now, therefore, it makes sense to wonder if we can find the minimal set of generators for a vector space. Okay, so let's assume that we have a subvector space of V. Of course, we can take as a generating set the whole subvector space. On the other hand, we can start removing vectors from it, as long as these vectors are linear combination of other vectors inside the vector space, and we will get ever smaller sets of generators. We wonder, is it possible to find in some sense a minimal set of generators so that we can represent these subvector spaces in a more efficient way? So, question, given a subvector space W in V, is it possible to determine a minimal set of generators for W? What does minimal mean? Minimal means that the vector space generated by these Wj's is the whole subspace W, but if we remove any of these vectors, any of the Wj's from this generating set, so if we consider the set Wi's for I different from some k, and we take the vector space generated by them, this will not be W anymore for any k. Okay, so if I just remove one of the vectors from this set, the remaining ones will not be able to generate the whole W anymore. Okay, this means minimal. So this leads us to the concept of basis. Therefore, this lecture will be on basis of a vector space. So first of all, we'll have to make an assumption that will hold throughout the course. So assumption: any vector space in this course will admit a finite set of generators. So any vector space in this course will admit a finite set of generators. So this property is referred to as a property for the vector space of being a finite dimensional. This means that any vector space will be finite dimensional. This is the definition of being finite dimensional. Okay, so this assumption is extremely important. Let's now give the definition of basis. This is an extremely important definition. So a basis for a vector space V is a set of linearly independent generators. Of V. In the next lecture, we will state the main results for a basis. There are two of them, and a few of their corollaries, and we will see why a basis is related to this initial question of determining a minimal set of generators for a subspace.